Welcome to this edition of AP Chemistry with the National Math and Science Initiative. My name is Renee McCormick, and I'm happy that you're here. So we're going to start today with electrochemistry, and electrochemistry is going to be broken into two files. Today's file will be all about galvanic cells, and we'll see how long that takes us to do. I am going to talk a little fast, despite the fact I am from Texas, and this is a Texas twang that is probably not going away. So I love electrochemistry. I love it for a couple of reasons. We do it early in the year because it's actually one of the easier units to master. Secondly, it's sort of relevant. It's relevant to what you do. You know about batteries and you know about electricity and things like that. What you may not understand completely yet are the chemical connections to such things. And so that's one of the reasons I really like it. Plus, it's easy. I wish we had a set of mnemonic devices and acronyms and easy little memory tricks for you for each and every unit that we do, but that's just not necessarily the case. But this one is particularly student-friendly, and I'm hoping that you enjoy it as much as I do. So as always, we start with some terms that you have to know, electrochemistry being one of them, which is just the study of the interchange of chemical and electrical energy. When you were a little kid, you learned that energy basically came in two forms, kinetic and potential, and unfortunately we focused your entire first 8 or 9 years of your schooling on just those two ideas, and the fact that potential was only actually dealt with as gravitational potential, not even electric potential energy. And it wasn't until you got into biology that you started to understand that a separation of charge across, let's say, the inner membrane of a mitochondria would actually allow for energy flow that could be used for useful work. So oxidation itself, we have a little oil rig acronym that helps us remember what's going on with oxidation and reduction. So oxidation is loss, O-I-L, and reduction is gain, R-I-G. I think it's an appropriate acronym, being that I am from Texas. There are many other ones. There's Leo goes grr, and in South Texas they often use the word ole, where a lot of the folks down there are native Spanish speakers. I wish I were. And it even looks like an electron there with the accent on the E being like the minus sign on an electron, but it's oxidation, loss of electrons. So when you're looking at trying to decide who was oxidized and who was reduced, it's often best for you to start here, because reduction is a word your math brain readily accepts as a number went down. So if you think about iron 3 ion, it could be reduced to iron 2 ion, and it could also be reduced all the way down to iron metal with an oxidation state of 0. Oxidation number is, again, that assigned charge on an atom, so +3 versus +2 versus 0, and no, it doesn't matter whether you write +3 or 3+. Oxidizing agent is the species that is reduced, and it's called an oxidizing agent because itself is reduced, which causes oxidation, and vice versa. A reducing agent is a species that is oxidized and thus causes reduction. So when we were doing redox equations not long ago, we often did this and this, just to label them right up front. When you kind of just get used to using that as a little template, you won't ever be confused about, well, who was the oxidizing agent? Oh, yes, that was the thing that was reduced. And so it's just a nice visual that kind of gets you started off on the right path. So electrochemistry involves two main types of processes. The process of galvanic or voltaic cells, which are spontaneous chemical reactions, or batteries, as you like to call them, versus the opposite part, in terms of thermodynamics, which is an electrolytic cell, when these are non-spontaneous and they require an external energy source, such as a direct current. That's what DC stands for, power source. And that could be your typical like flashlight battery or transistor radio battery type thing that can give off a direct current as well. But both of these fit into a big umbrella kind of term category called electrochemical. So again, electrochemical breaks out into two pieces, those that are spontaneous and those that are non-spontaneous. There were two scientists, Alessandro Volta and Luigi Galvani, who, that's what these names are actually from. They're honoring those two gentlemen. And they figured out how to make batteries. So these are what you think of as a battery, and this is what you think of as a power source. Then we have a whole nother set of terms, and these are the actual parts, or the anatomy, if you will, of the galvanic or voltaic cell. So there is an anode, and there is a cathode. These are words that you may have heard of before. Matter of fact, you may have heard of the words anion and cation, which are related to these two words, and we'll make those terms perfectly clear in a bit. But the anode is the electrode where oxidation occurs. So anode and oxidation. And after a period of time, the anode may appear to become smaller as it falls into solution. So you can think of it as dissolving. In other words, if I had an iron one, it could be going to this, which is where it would go first. And if I keep going with this cell, it would ultimately end up losing yet another electron, and the ions would become Fe3 plus electrons, or ions rather. The cathode is the electrode. There's a typo. The electrode where reduction occurs. After a period of time, it's going to appear larger or more massive, or it's going to have plating taking place or crumbly bits attached to it due to the ions from solution plating onto it. So this one gains mass. And you're going to be glad you know that. Trust me. I've seen your test questions. All right, inert electrodes. Inert electrodes are used when a gas is involved. So we don't have a chunk of metal that is our ultimate goal or our ultimate beginning. Or we're going from ion to ion. So if I just went back and forth between Fe2 plus and Fe3 plus, I would use an inert electrode. Because if I use iron, the metal, as an electrode, I'm going to go all the way to Fe0. And so these are often made expensively of platinum or cheaply of graphite. And you can actually make your own inert electrodes by taking old-fashioned wooden pencils, popping the eraser end off of a wooden pencil and sharpening both pieces, both ends of that pencil, and grasping on with an alligator clip to each of those pieces of what we call pencil lead, but really it's carbon graphite that's within that wooden shell that we call a pencil. Also, there's a salt bridge, and this is a little device that is used to maintain electrical neutrality in a galvanic cell, meaning balance the charge. We're going to have ions moving, and so we need to balance that charge. And this can be filled with agar, think petri dish, think biology, think that jello-like stuff that we have in a hot solution, pour it into a petri dish, and then let it gel, literally, kind of like jello. And it contains a neutral salt, or it could be replaced with something called a porous cup. But neutral salts are more common in the laboratory. We also talk about the electron flow. The electron flow is always from anode to cathode through the wire of the external circuit. The external circuit. Then there is what we have called standard cell notation, line notation. Think of it like an ion sandwich. Basically, we're going to start with the anode, then the ion in solution for the anode, and then the cathode and the ion, or the cathode solution, the ion for that as well. Let me try that again. Can I start over? We have the anode, then we have a solution that contains the anode, the ion associated with the anode, and then we have the ion associated with the cathode, and then the cathode itself. So for instance, zinc. So if we were using zinc as an electrode, we would have the metal zinc, and it would be the anode. These go in alphabetical order. Anode, it starts with an A and comes before cathode. Then we would have the ion of the anode. If it's at standard conditions, that concentration would be 1 molar. Then we use these double lines, and then we have the ion of the cathode, and then we have the cathode itself. So it always goes metal, ion, / ion, metal. Now, a voltmeter is simply that. We have a lot of ohmmeters in our life. A thermometer or a thermometer was one of the first you were ever introduced to as a child. But now we have a meter that can measure volts. We call it a voltmeter, aptly named. And it measures the cell potential, which is the electromotive force, also symbolized by a curly QE. And it's going to be measured in the units of volt, named after Volta. So let's start out by just kind of dusting off some cobwebs. We've already gone through being able to balance reactions, especially redox reactions. So we're just going to run through a quick example just to kind of remind you of how that works. We're looking for something to be reduced and something to be oxidized. And so I always look at whatever's simplest to my brain, and I'm looking at those two irons going, okay, I get what's going on there. We went up in charge from a +2 for this iron to a +3 for that iron. So going up is an oxidation. It's certainly not a reduction. So I'm going to start there. So Fe2 plus is going to go to Fe3 plus. Meanwhile, MnO4, the other player in this scenario, is going to go to Mn2 plus. You like the way I wrote MnO4 minus in purple because it's actually purple in solution. Alright, so I'm going to come back to my iron and do it first since it's easy. Total charge on the left is +2, total charge on the right is +3, and all I can do in this scenario is add electrons. So I'm going to add a single electron to make +2 charge on both sides, and I now have a balanced oxidation, half reaction. That means that iron 2, the reactant, is my reducing agent, if anybody asks me. Notice that I didn't have to go all the way to 0. I just have to get the charge balanced on each side of this half reaction. So we call that the oxidation half reaction. So back up for the permanganate. I have 1 Mn on each side, which is fine. I have 4 O's on the left and 0 on the right, so I rectify that by adding 4 H2O's to get my 4 O's. And now you've gone and done it. Now you've introduced H's on the right, and you had no H's on the left, but that's okay, because if you remember your oxidation reduction rules, you can add as many H pluses as you'd like. So I would need 8 of them, please. Now the total charge on the left is a +7. The total charge on the right is a +2. So I need to add, let's see if I can squeeze these in, 5 electrons to that side, and now I have a total charge of +2, correct? Yes, +2 on each side, so we are now balanced. So overall, the goal is to slash off electrons of equal quantity. So I've got 5 electrons here, but only 1 sad electron here, so I must multiply this entire equation through by 5. So I can go slash, slash. So N equals 5 electrons. I get in the habit of doing that because that N is going to become very important to you in about an hour. So my overall reaction now, is there anything else I can clean up? Nope. H pluses don't occur on both sides of the arrow. Waters don't occur on both sides of the arrows, so I'm stuck with what I have at this point. So my overall reaction is going to be the permanganate ion, which I remind you is purple in solution, plus 5 Fe2 plus ions, plus 8 H plus ions. I think I got it all. Got that, I got that, I got that. Time for an arrow. It's going to go to Mn2 plus ion, plus 5 Fe3 plus ions, plus 4 waters. And now I know in first year, maybe even earlier in this year, you were taught to make a little checklist of I have 1 Mn on each side, I have 4 O's on each side. You don't have to do that. I'm just telling you, if the charge balances on the left and the right, you're done. So my total charge over here on this side of this equation is a -1 for that permanganate, plus 5 times +2, so plus a +10, plus a +8. And that totals +17. I'm looking for +17 on this side. Ooh, this side's easier. Waters are neutral, and I got a 2 plus, and I have 5 times the 3 plus, for a total of 15 plus 2, which equals 17, and we're golden. So this is a balanced reaction. Takes a little while. These are going to be multiple choice questions that are going to take you a little while. So you do need to practice those and get your speed up. So now, talking back to the electrochemistry of it, if we place that permanganate ion and iron 2 ion in the same container, the electrons are going to be transferred directly when the reactants collide. Well, that's no fun because we can't get any useful work out of that. We cannot exploit that concept into making our lives better. We want useful work from this situation. So what we really want to do is not let all of that useful work be released as heat, but we want to harness it. So we can harness this if we separate the oxidizing agent from the reducing agent. That's going to require the electron transfer to go through a wire. So this is some engineering in action here. If we do that, we can harness the energy and make it run a motor, light up a light bulb, run a cell phone, for crying out loud. Just about anything we want it to do. So the idea here is to get sustained electron flow, and that cannot occur in our first picture, which is, oh, let's go in the wrong direction. I'm so sorry. Our first picture right here. Sustained electron flow cannot occur. So electron flow cannot occur. If we want electron flow to occur, we've got to fix this. So the big question is, how do we fix this? Well, we insert a salt bridge, and its job is to balance the charge. I want you to embrace that phrase and use it in your writing. Never ever say complete the circuit, always say balance the charge. So you do this using an electrolyte. Okay, electrolyte is code for charged and mobile. Ions make great charged mobile species. So charged and mobile. Got to have moving pieces that can carry a charge in order for electricity to flow. So this is usually in a U-shaped tube that we fill with agar, has the salt dissolved into the agar before it gels, and it is inverted then and connected over into two compartments. You can just think of these as two separate beakers for lack of imagination. They can be fancier than that, but that's pretty simple. And what it does is it keeps the cell neutral. So our favorite salt to use is potassium nitrate because it's danged soluble. It doesn't precipitate with anybody, which doesn't screw up our results later. So it's a safe one to use. If you get to design something, use potassium nitrate to do it. So potassium nitrate, that way you don't get any precipitation. That's the big deal. Now we can also do this with a porous cup or a porous disc. But that's going to be some pretty fancy glassware to have this little bridge going across here. But we still need a barrier. And so that says porous disc right there. So we still need that barrier. Now, cell potential is symbolized by a whole bunch of different things because, you know, that's just the way your life is. There are a lot of grown-ups that have been writing this stuff into literature for the last century, and they just can't all get along on some symbolization. Unfortunately, there's all different symbols in all different books, and the AP exam's a national exam written by at least 6 different people. So we have E cell, we have EMF, or we have a fancy curly Q E cell. But all of those are the same thing, and they're a measure of the electro, as in electron, motive, as in moving, force. And you may want to think of it as the pull of the electrons as they travel from the anode to the cathode. And we'll talk about why they travel that way in a few minutes, because, you know, I'm kind of big on the why thing. All right, so just still getting the lingo here. Volt, a volt, which is symbolized by a big capital V, and pretty much everyone agrees on that at least, is the unit of electric potential. I remind you, potential is separation. When you were a little kid, you thought about potential energy as how far you could separate a book from the floor and then drop the book. And it would release its potential energy and make a big loud sound. And the higher you dropped it from, the better the sound, because it converted all of that energy into sound energy. So when we talk electric potential, we're talking about a separation of charge, pluses versus minuses. How far apart can you get them? So the volt is equal to 1, how many? 1 joule of work per coulomb of charge, which looks like this, a joule per coulomb. And that's the same thing as a volt. And you can interchange these two symbols in your dimensional analysis until you're happy. A voltmeter, go figure, is a meter that measures voltage. So it measures electric potential. Of course, there's going to be some energy lost as heat. You may have had a physical science course, or you may be in physics, and you may have heard about resistors. So anytime we move electrons, we meet with resistance in that motion, and that usually is lost as heat due to friction. And so that keeps a voltmeter reading just a tad lower than the actual or calculated voltage. And digital voltmeters have a lot less resistance than the old-fashioned analog or read this needle on a scale kind. And if you want to get picky and eliminate the error introduced by resistance, you attach a variable external power source called a potentiometer. Nobody's going to ask you this, okay? This is just for your edification. A potentiometer, and adjust it so that the zero current flows. And the accurate voltage is then equal in magnitude but opposite in sign to the reading on the potentiometer. Now, standard reduction potentials. you're going to work with these a lot, so pay attention. You're going to be glad you did. Each half reaction has a cell potential. So when I did that permanganate thing and that iron thing earlier in those two half reactions, each one of those I could look up their potential on a table. You need at this point to make sure that you have sitting in front of you the College Board periodic table of the elements, so the periodic table from the College Board. That's the one you have to use on your AP exam, so I want you to become uber familiar with it. And also your standard electrode potentials, and that's also from the College Board. Now we're going to have to refer in some of these example problems to some fancier potentials than this because the College Board one is oversimplified, but anything we need is contained within these notes, or so she says. We'll see. Okay. So each of those half reactions has a cell potential, and each potential is measured against a standard, because that's how we do things in chemistry. For instance, the standard we measure everything by on the periodic table is the isotope carbon-12. But this standard hydrogen electrode consists of a piece of inert platinum that's bathed by hydrogen gas at 1 atmosphere, and the hydrogen electrode is assigned a value of exactly 0. So hydrogen, very simple element, but the tricky thing is it is a gas at laboratory conditions. Speaking of laboratory conditions, humans are grumpy at STP. Now I know when you learned gas laws back in first year, you learned about STP, standard temperature and pressure, which was 1 atmosphere and 0 degrees Celsius, but humans are grumpy at 0 degrees Celsius. So standard conditions allow humans to be much happier at room temperature, which we'll define as 25 degrees Celsius. Add 273 to that and you get 298 Kelvin. If a solution is involved, its concentration will be exactly 1.0 molar. And if gases are involved, we'll define them as 1 atmosphere pressure. And then the word naught, N-A-U-G-H-T, which I know with my Texas twang sounds more like not when I say it, but I try really hard to pronounce it as naught and really lengthen that A, but it's hard for a Texan. So that little 0, that little naught, that thing right there is naught. And we use the naught to symbolize standard conditions. And when we do thermo, if you've done it before you got here or if you're about to head into it next, thermo is riddled with this naught as well. But the good news is it still means the same thing as standard conditions, where we have 298 Kelvin, 1 atmosphere, and 1 molar concentration if solutions are involved. So that means that all of these symbols right here can become standard symbols if we simply put the naught on them. Then you may have seen delta H or delta G, and we can do the same with them, but only use the naught if you mean it. If you mean 298, 25 degrees Celsius, same thing, 1 atmosphere of pressure or 1 molar concentrations of a gas. So that naught can actually be your friend when you're wondering, what's the temperature? Oh yeah, 298. What's the concentration? Oh yeah, 1 molar. Now, we'll remove the naught if we change the conditions to non-standard conditions. The naught will be out of there. So you'll see these symbols written both ways. You need to pay attention. So the diagram that we have over here to the right illustrates what really happens when a galvanic cell constructed from zinc sulfate and copper 2 sulfate using their respective metals as electrodes. Notice that 1 molar solutions of each salt are used, so that liquid, that solution that those electrodes are immersed into, have loads of ions floating around. Notice an overall voltage of 1.10 volt for the process. We'll get to how that happens in a second, because we'll learn to read the reduction potential chart. So what we're saying here is on this zinc, literally, if electrons are moving that direction, I'm going to change to red. If electrons are moving in this direction, which trust me for now that they do, they move fat cat from anode to cathode. That says anode and that says cathode. Then what's happening is an electron comes off of the zinc atom, making a zinc 1+ ion, which you've never heard of before, and a second electron comes off, making a zinc 2+ ion, which goes plop down into solution. So electron, electron, plop, zinc ion. Electron, electron, plop, zinc ion. Electron, electron, plop, zinc ion. Meanwhile, as each electron-electron pair is leaving the zinc, it's moving over here into this solution, being conducted down this piece of metal into this solution, where now those ions, those copper 2+ ions, remember this is 1.0 molar copper 2 ion, and this is 1.0 molar zinc 2 ion. So incoming electron, atom. Incoming electron, atom. So as the electrons are coming in, the copper ion is now being attracted, and it's going to make an atom and fill that spot. Whereas this zinc atom is vacating the spot on the other side to become a zinc ion. And that's really critical, and you haven't heard me explain that for the last time. We'll explain that over again, give you a couple shots at it. So here's the important stuff that you need to know. Elements that have the most positive reduction potential are easily reduced. In other words, they get to be reduced when you're trying to decide who's reduced and who's oxidized. They are easily reduced, therefore get to be reduced. That's how you get started. When you're scratching your head wondering where to start, that's how you get started. You compare the reduction potentials, and the more positive one gets to be reduced. So elements that have the least positive reduction potential are easily oxidized. So that makes sense because these are opposite concepts. The converse must also be true. So the table, this reduction potential table we're about to analyze, can also be used to tell the strength of various oxidizing and reducing agents. So it can also be used as an activity series. Metals having less positive reduction potentials are more active and will replace metals with more positive potentials, which makes sense if you think about it. Now, how can we determine which substance is being reduced and which is being oxidized? Again, I say the more positive reduction potential gets to be reduced if you are trying to set up a cell that can act as a battery. So we will refer to this table over and over and over again. Print the file reduction potential table from the website where you found this, which was apchemistry.nimsy.wikispaces.com from the wiki page. Go back to the wiki page and get it, because we're going to be using it. Now, here is one that some of the example problems needed. So this one is stolen straight out of a book, zoomed off 5th edition, where all of the example problems have come from. Well, not all, but most, I should say. So we'll refer to this little table from time to time. So we'll just scroll back to it when we need to. It'll make you a little dizzy, but that's okay. You'll get over it. Alrighty then, let's keep going. Calculating the standard cell potential, which is symbolized again by this, or this, or this, because grown-ups in your life cannot get along. The first thing we need to do is decide which element is oxidized or reduced using the table of reduction potentials, and the more positive reduction potential gets to be reduced. Then we will write both equations as is. In other words, don't get creative. Just pick them up off of the chart with their voltages. Then we will reverse the equation that's going to be oxidized and change the sign of the voltage. So it's no longer E naught reduction potential. Then it's going to become E naught oxidation. That's an O. Oxidation potential. When you change the sign. Change sign. Then we're going to balance the two half reactions, but you do not multiply voltages. How come? I know you're wondering. How come? Because remember that a volt is a joule per coulomb, which means it's a ratio. So doubling a ratio does not change a ratio. Tripling a ratio does not change a ratio. It's still a ratio. So we don't ever multiply those voltages. But we will add the two half reactions and the voltages together, remembering that you change the sign of the oxidation one. And it's just that simple. I know that, somebody once may have told you that chemistry was hard or confusing or difficult. Well, that's just because you didn't have the National Math Science Initiative helping you out. So we're pretty clear communicators. So remembering that naught means standard conditions. So let's recap some of the mnemonic devices that come in handy while doing this. Again, I say, I wish I had a cute little list like this for every one of the units that you're going to cover this year in this course, but I think this is what makes this one just a piece of cake to accomplish and to master. Mnemonic devices. Okay, that's a big teacher word, which means I'm going to give you a series of something that's going to help trigger a whole bunch of information running out of your head. For instance, if I say Roy G. Biv, you memorized red, orange, yellow, green, blue, indigo, and violet, which actually is not just the colors of the rainbow, it's the colors of the rainbow in order by wavelength or frequency, which are opposite concepts, whichever direction you want to take off, from the violet end or from the red end. But it sure is handy to be able to remember them all in order using Roy G. Biv. You may have also learned one for taxonomy in biology. Since I'm from Texas and my AP biology teacher had us make up our own, mine is kickers prefer chewing organic, fresh-grown skull, which is kingdom, phylum, class, order, family, genus, species, in that order. So when I say mnemonic devices, it's just silly little things that help you remember a whole lot of information. So anox. Anox stands for oxidation. Get the ox part. Oxidation occurs at the anode. And again, this may show a decrease in mass. Red cat. Reduction occurs at the cathode, and it's going to show an increase in mass because you're taking a metal ion with a positive charge, or 2 or 3, and you're going to reduce it down to, most likely, to an atom. And if it goes that far, you will see a show. It will show an increase in mass. That's why the word may is there, because if I just went, instead of all the way to the metal and went to like the 2+ ion, it's still a reduction, but those are still in solution, so that's not going to affect the mass of my electrode. And then fat cat, from anode to cathode. From anode to cathode is the path that the electrons flow. So it's the electron flow, and they always flow this way, from anode to cathode. The word cathode itself, if you write it like a second grader, that T looks like a plus sign. So the cathode is positive in a galvanic or voltaic cell, and that means that the anode must be negative. Anode, therefore, is negative. The salt bridge is the bridge between the cells whose purpose is to provide ions to balance the charge, and it's usually made of a salt-filled agar in a 1.0 molar solution as well. So you make your agar with a 1.0 molar solution of your salt, and potassium nitrate is by far our favorite. You can use sodium nitrate as well. It's okay. We just need something that's uber soluble. And then EPA, in the second half of this unit, we'll get to the fact that in an electrolytic cell, there is a positive anode. So here are just two different artist renditions, one fancier than the other, that shows what's going on. So if we look at zinc and copper, let's figure out what the scoop is. I am now looking at my reduction potential table. I am scanning it. I'm looking for zinc. I'm looking for copper. It's a reduction potential table, so these will both be reductions. So zinc's reduction is a negative 0.76 volts. And copper is a positive, I'm still looking for it, but I know it's a positive, and I'm thinking it's a 0.34. There it is. Copper 2. Yes, I see 2 charges right there. So copper 2. So copper 2 plus zinc 2 plus, written as reductions going all the way to their metal, this one is a positive 0.34 volts. So who would be the most positive? Not a trick question. Indeed, it would be the one with the positive value. So this one, copper, is going to be more positive. What does that mean? Therefore, it is reduced. Okay, if it is reduced, here's my copper electrode right here. There's my copper electrode. If it's being reduced, then red cat applies. So that's the cathode. And cathodes are positive because of that T sitting in the middle of the word written like a second grader. So it makes perfect sense that the electrons are going to be drawn to that positive electrode. If this electrode right here is positive, wouldn't negative electrodes be attracted to it because opposites attract? So if that's the case, then this is the reaction that's going to take place. Every pair of electrons that come in are going to react over here with this copper 2 ion and make a copper atom, and that atom is going to stick to that electrode. So reduction occurs at the cathode, that's red cat. Anox is going on over here at the anode. Electrons are going to leave here and go that way. Where the electron's coming from, they're coming from a zinc atom that's in this chunk of metal that is the electrode. And so for every pair of those electrons that leave, then I'm going to have a new zinc 2+ ion, which means that negative ions have to flow out of the salt bridge to neutralize that and keep the charge on both sides of this balanced. And so negative ions are going to come out of here, and positive ions, conversely, are going to come out of the salt bridge here, because if two electrons come in and those two electrons match up with a copper ion that's floating in solution to make that atom, then I got to replace them with two positive charges. If we don't keep the charge balanced, the electrons can't flow. They'll build up on one side and our battery is what we call kaput. It won't work anymore. Alright, so here's a fancier rendition on the other side. It's the exact same reaction that's taking place, even kind enough that I found two pictures where zinc's on the left and copper's on the right, but please don't think it's always that way. These are beakers. They're beakers on a table. This is an artist's rendition. It doesn't always get drawn this way. You can walk around the table and the artist would have a separate perspective. So this one just has a fancy little switch in it, no big deal. When the switch is closed, again the electrons flow. We can see that by this balanced equation right here, that two electrons are going to be given off, and more zinc 2+ ions are going to start falling in here, which means I've got to have some nitrate ions that are going to come and actually neutralize them, a pair of nitrate ions for each zinc 2+ formed, and vice versa. I've got some copper going on this side. When these electrons are coming in, two electrons, as it shows us right here, are going to react with the copper 2 ion and make zinc atoms. So that's why we say the cathode gains mass, because we're making atoms from ions. The anions from the salt move to the anode. Look at that. Long a time ago, you took on faith that an anion was a negative ion. Now you know where that word actually comes from. Anions migrate to the anode, and cations migrate to the cathode. They are aptly named. We just withheld that information for about a year. You'll hear other confessions. We chemistry teachers, we lie to you a little bit in first year because we have to talk in generalities, and then you find